All right, so we are in chapter 10 of the parent class, the last chapter that we cover, and we deal with counting problems in that section. It's a very big part of mathematics called combinatorics that deals with counting problems of those sorts. And what I want to do today is just do a little bit of practice with the things we're already learning in that class. In particular, I want to focus on how to compute factorials, and I want to do a couple of examples of counting problems as well. So these are all kind of basic as far as chapter 10 goes. And then next week we'll look at some of the more complicated types of counting problems. But to begin with, we have some computations that we're asked to do, all involving factorials in some way. So starting with the first, we're looking at 5 factorial. Remember, that's what that exclamation point means. The meaning of that word factorial, or that symbol for factorial, is that we take the number that we're given, 5 in this case, and we multiply it to every natural number that's less than that value. So basically starting at 5 and counting our way down to 1, multiplying everything along the way. And you could definitely do this in a calculator if you wanted to, or it's kind of a nice exercise to see if you can use some arithmetic tricks to help with these. So for example, 5 times 2 I know is 10, and 10 is a really nice number to work with when multiplication is involved, because 10 times any number is just that number with a 0 at the end of it. I also know that this 1 here, if I multiply anything by 1, it's not going to change the result, so I can actually kind of ignore the 1 altogether. So 5 times 2, I know that's 10. I'm going to ignore the 1. 4 times 3 is equal to 12, and then again, using that trick with multiplying a number by 10, I just take that 12 and put a 0 at the end of it. So this is equal to 120. And like I said, yes, you could easily do this in a calculator, but it's more useful for these types of problems to, it's more instructive, I should say, to try and work through it on your own, because there's tricks that tend to make it work a little easier than you might expect. Now, this problem right here, 10 factorial over 8 factorial, we're going to see things like this a lot in chapter 10, where we have a quotient. Remember, that's a division problem where your numerator and denominator involve factorials. Notice this one here has 2 factorials that are being multiplied in the denominator. These types of problems arise naturally when we talk about combinations and permutations, which most counting problems that you would encounter in a class like this one will be of those types. So being able to calculate these is really important. Now, 10 factorial is an enormous number. 10 times 9 times 8 times, and remember, this just kind of goes all the way down to 1. I don't feel like writing all of those numbers, so I'm using an ellipsis right here. You know what that means. And then I'm going to put that over 8 factorial, which is another really large number. 8 times 7 times, and then this is going to go all the way down to 2 times 1. Now, it is not worth your time and effort to actually multiply all of these out, because there's a whole lot of cancellation that also happens here. Notice I have 8 times 7 times 6 times 4, or 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all appearing right here. And those are the exact factors in this product down here as well. And because I'm dividing, all of these guys will cancel with all of those guys. There is no need to actually multiply that out, because after canceling, all that's left is 10 times 9, which is 90, right? So if I did this the long way, I would have spent a bunch of time multiplying this out, getting a huge number, multiplying this out, getting a huge number, and then dividing a huge number by a huge number, and it's completely unnecessary to do all that work. So please take note of these tricks, okay? This problem is very similar to this one. So again, 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm going to use the dot, dot, dot again. Over 5 factorial, which is 5 times 4 times 3 times 2 times 1. Probably could have just included the 3 in there. That's all right. And then I'm multiplying that by 2 factorial, which is just 2 times 1. Okay. Now in this case, I have 5 times 4 times 3 times 2 times 1, which also appears right here in my numerator. So as before, I get to cancel all of those with all of those. Now down here I have 2 times 1, and as before, the 1 doesn't really contribute anything, so just think of this as 2. And up here I have 7 times 6. I could do the multiplication and then the division if I wanted to, but notice that 2 shares a factor with 6, so I can do some canceling here as well. 6 divided by 2 is 3. So that all that's left, I have nothing left in the denominator except the 1, and then in my numerator I have 7 times 3, which is just 21. These problems are much easier than they might initially appear if you use these tricks, so it's very important to know these tricks. Okay? Excuse me. So next problem we want to look at. If 2 dice are rolled, how many ways can the sum of the results be greater than 9? Okay? Well, in the parent class in section 10.1, we talked about a similar problem where we want to determine the total number of possibilities if you roll 2 dice. And we made a grid, and we found that there were 36 different ways that those can be that 2 dice can be rolled. We're placing a condition on the results of the roll of these 2 dice, though. So I want to determine how many different ways these 2 dice can produce a sum of some number greater than 9. Now I know that if I roll 2 6-sided dice, and it's assumed that these are 6-sided, even though I didn't say that, we know that the largest sum you can get by rolling 2 dice is 12, because that would be if both sides showed a 6, the largest possible number. I can also roll an 11, and I can also roll a 10. Those are the 3 possibilities that we want to consider, because anything else would not be greater than 9. So I'm going to look at all the different ways I can roll a 10, all the different ways I can roll an 11, and all the different ways I can roll a 12. Now, one way of rolling a 10, and I'm going to use ordered pairs to signify this, is if I roll a 4 with one of my dice and a 6 with the other. 4 plus 6 is 10. Okay? Another way of rolling a 10 is if both dice are 5s. And then finally, another way of rolling a 10 is if my first die is a 6 and my second is a 4. And we count these as different possibilities because I'm thinking of one of my die as being the first die, and then my other one being the second. So if my first is a 4 and my second is a 6, that's technically different than my first being a 6 and my second being a 4. There are 3 possibilities of how I can get a 10 here. And you should verify for yourself that if either of my die are a 1, a 2, or a 3, it's impossible for the other die to be anything that would get me a sum of 10. So this is all the possibilities. For 11, the only possibilities are if I roll a 5 with my first die, 6 with my second, or if I get the other way around, 6 and 5. Okay? Verify for yourself that these are the only possible ways to get an 11. There's only one way to roll a 12, and that's if both dice are 6s. Okay? So this is what we call counting by systematic listing, and that's where we list all of the possibilities by working through them in an exhaustive way. Exhaustive means you don't miss anything. So I have listed out all of the possibilities, and there are 3 plus 2 plus 1, which is 6 ways of rolling a sum greater than 9. Okay? Systematic listing is one of the most direct and straightforward ways of handling counting problems like this, but they're not terribly useful for most counting problems. And the reason for that is even if you're looking at a problem where systematic listing is possible, it's likely that there would be many possibilities that you have to list, and you end up putting way too much time into that one problem. That's why we develop more efficient techniques for dealing with other types of problems. Okay, here's the last one I want to look at. And it says, how many different ways can 6 DVD cases be arranged on a shelf? And basically what we mean by this is we have 6 different DVD cases, and we want to line them up 1, 2, 3, 4, 5, 6. And we can rearrange their order any number of ways, but what we want to determine is how many arrangements are possible. So this problem ends up being a factorial problem, and we talk about why in the parent class, but I want to reiterate why here. This begins with what we call the fundamental counting principle, or the multiplication rule. If I think of the 6 possible positions that I can place my DVDs as being represented by these little underscores here. So I'm going to put a DVD here, I'm going to put one here, I'm going to put one here, here, and here, and here. Before I have placed any DVDs anywhere, I have 6 possible choices for which one goes here. Okay, so I'm going to represent that by putting a 6 here. Now, the multiplication rule, or the fundamental counting principle, says that if you have 2 or more events that are independent of each other, and I'm not going to get too deeply into what that means, but in this context, it works. If I have 2 or more events, and there's a certain number of possibilities for the first event, and then a different number of possibilities for the next event, and so on and so forth, then the total number of possible ways of selecting those events is the product of the number of possibilities of all of the individual events. So that's a very strange way of kind of explaining it, probably confusing, but the way this is going to play out here, if I have 6 choices for my first DVD, then once I have placed a DVD there, I am now left with 5 remaining DVDs, of which I can put 1 on the second position here. So I have 5 choices for this next position. Once I've placed a DVD there, that leaves me with 4 possible DVDs to put in this position, and then 3 left here, 2 choices here, and then once I have selected my first 5 DVDs, I'm only going to be left with 1, and that's the only possible DVD case that can go there. The fundamental counting principle says that I multiply these numbers together to get the total number of arrangements of these DVDs. Notice, however, that that's the same thing as 6 factorial. And this is why we care about factorials in the counting problems that we see in this section, because factorials represent the total number of arrangements of a certain number of objects, that number being given by whatever we're taking the factorial of. So I'm trying to look for how many different arrangements of 6 DVD cases exist. It would be 6 factorial. Working this out is not difficult. Notice we've already done 5 factorial up here. 5 factorial was 120. And notice 6 factorial is just 6 times 5 factorial. Here's 5 factorial right here. So that's 6 times 120. I'm using the work that I've already done. Think of that as 6 times 12, which is 72. Put a 0 at the end and we get 720. Okay? Like I said before, this is kind of reiterating things we've already talked about in the parent class. So hopefully this just helps kind of support that material. But that's all we're going to look at this week.